Hey, my name is Dave Anselmi. I'm the product manager at Clustrix. We create a database, which is a scale-out replacement for MySQL that allows you to continually add nodes to gain more write and read scale. So it's a full scale-out solution. Today we wanted to talk about, for a lightning webinar, for about 10-15 minutes, why durable AI network isn't truly durable. If you understand how this web conference thing goes, you can type in questions at the bottom of your screen, however, and we'll get to them at the end. Thanks. So today I wanted to cover, just as a high level, what is durability? What does that even mean? Why is it important? How does it work? And why this even matters, especially with the great timing of last week, as you saw on Tuesday, Amazon did have a significant outage. So durability is something that comes up a lot in a relational database. Now, a relational database is something, a concept that's been around for quite a many number of years, maybe 40 or so. It is the underpinning of any kind of major database that wants to do high-value, high-volume transactions. Something that has to do with money is typically the way to describe this. So anytime you go to an e-commerce site, anytime you're doing a trade on a bidding or a trading site, anytime you want to send in data, the data has to be confirmed that two different people want it at the same time. One of them has to win and one of them has to lose. This kind of information, in order to guarantee that transaction, is a concept called ACID. ACID means atomicity, consistency, isolation, and durability. Relational databases typically have ACID, and NoSQL databases don't. NoSQL has their version of this they call base, which is basically, it means it is eventually consistent. Eventually, it's going to be durable. The data is able to get in very, very fast. They've made a trade-off of speed for the ACID compliance. Let's get into what ACID compliance means. So first, atomicity means all transactions are all or nothing, which means, in other words, if one part of the transaction doesn't work like it's supposed to, the rest of it's going to fail, and vice versa. So, for instance, if I have a transaction that says update this, read from this, and then update this, depending on the read, if any of the previous statements excuse me, in that transaction fails, that means all of them fail, and the entire transaction rolls back. You don't want to have a single transaction with multiple statements to have multiple of those statements clear and the rest of them don't, and then say, okay, this transaction is sort of okay. So transaction has to be complete or completely not. The second one, for consistency. Transactions must follow the data validation rules of the system. So for instance, you have a thing called a trigger. That means the database knows that if I make an update to this table, then it's going to automatically do some other updates for me. This is how you can implement business rules in the database so that even though you have multiple application programmers working on your system, they don't have to know all the business rules. Like, for example, in a classic case for CRM, for customer relationship management, I shouldn't have an order if I didn't already have an opportunity. I shouldn't have an opportunity if I can't have a deal, for example, if I don't have an opportunity, and I can't create an opportunity if I don't have a lead, and vice versa. You work your way back. When you transfer to CRM over to enterprise relationship management, you can say you can't have an order unless you have that opportunity. And before you can have the opportunity, you need to have the lead, obviously, and the deal creates the order. Each of those are, if you will, a prerequisite in the business rules, and by putting them in the database, it keeps somebody from skipping steps and making mistakes. So consistency. Now, consistency matters even more when you have what's called a scale-out database. When you have multiple nodes on multiple different servers all working together with the database, it becomes a lot trickier to have the same data across multiple nodes. MySQL and other monotonic systems, SMP they call it, symmetric multiprocessing, but it really means a single master that takes writes and multiple potential read slaves. This is a lot easier there because there's only a single place where you do updates. So I don't have to guarantee a consistency between two different nodes unless I connect that system in a system called master-master. Then I have two updates in two different places. But then the database itself can't guarantee that consistency, and you have what's called conflict resolution that needs to be created, and it has to be created outside of the database at what we call the application level. So again, a single master system doesn't have to worry about consistency between multiple writes, but it does, at the application level, matter if you're consistent between the write and the read slave. The read slave is going to have some sort of lag, some sort of latency. And so you have a quick update scenario transaction, then the read slave can fall out of tune. And what will happen there is, for example, on an e-commerce site, when you go to add something to your cart, when you get to the actual checkout process, the system knows, and when I say the system, I mean the application, do not read from that read slave anymore. Because if there's any kind of lag, if somebody changes the item in their cart and then says, okay, check out immediately, if it's reading every read from the read slave in order to take pressure, take capacity off the write master, you might have made a change of your update of your cart, and then you say commit, you say check out, and the read slave doesn't get that update yet. So you might have made an update, so I wanted to buy 5, and the system says, fine, we can sell you 5. And you say, actually, I want 10. Okay, buy. If the system isn't going off the write master, it can't check the inventory versus available to promise and confirm, oh, wait, you can't get actually 10. We have 5 in back order. So on smart systems that work in high-value, high-volume transactions, they are going to make sure that you do not go off something that can be inconsistent. And so with a master read slave topology, it's going to make sure you stay on the master. Or with a multi-server system, MPP system, when you do that, that system must make sure that you have that consistency across all the nodes. The I in ACID means isolation, the ability to concurrently process multiple transactions in a way that one does not affect the other. And so you make sure, for example, the same thing with consistency, the available to promise matches the actual inventory. In that case is you have 2 different people trying to do a transaction. If you have 10 things in your available to promise, one of them person wants 6, the other person wants 4, it really depends if person A or person B hits commit first or hits buy. The system will run each of those transactions separately and then try to confirm if the system actually has the available data. So if both of them hit it at the exact same time, that's where you need the system to do a timestamp and say which is the one that actually hit exactly. It's impossible for both of the transactions to commit identically, so whoever gets to commit first gets the available. If the first person gets 6 and the other person wanted 4, they're both going to get it if it's 10. But if they have one of them wanted 6 and the other wanted 5, person 6 is going to get 6, person 5 is only going to get 4 of them. And finally, durability, which is what we're talking about today. This makes sure that the transactions that have been communicated by the database back to the application layer, if the database says this is committed, that means, yes, I've taken this transaction, that data better be there. If I unplug the system and walk away, if the system crashes, if the cloud has an outage like S3 did last week, that data needs to still be there when the outage is complete and the servers come back. Back in the day when we had very big servers with very large companies like Oracle, they'd literally walk in there and start yanking the power connectors and watch the systems crash and then say, okay, you got an hour, bring this thing back up. I want to see all the transactions there. You need to make sure when you're building a database that takes transactions that are important, that the transactions are maintained after an outage. So let's drill it a little bit more into durability. Ensuring the data is really on disk. So in e-commerce, the orders placed are still there, and the financial payment transactions really have cleared. You ensure what we call a single source of truth, that you can trust this thing. The database comes back after an outage, there aren't competing versions of the data. For example, if you had one person that said, I wanted to do a checkout of 6 items, and the other person that said 5, and I only had 10, I don't want to see 2 different orders in the system, one for 6 and one for 5. Without the system knowing how to handle the overage and telling the one person to get a coupon or telling the one person your item's on back order. A very classic example that happened back in the late 80s is the California Department of Motor Vehicles had multiple versions of your home address for each of the different actual applications they had in the system. One of them was your voter registration. Another one was tickets. Another one was license renewals. Another one was, I don't know on the top of my head, but that's at least 3. And what would happen is they'd capture your address each time. So it turned out that if you paid your latest license fee, that you'd have your home, and you'd moved, your home address would get changed there. Then if you had a ticket, your home address would get changed again. If you had to change your voter registration, it would change again. And you literally could have 3 different addresses for your stuff to go to. This is exactly how you don't want to have a database work. You want a single source of truth. If they confirm I'm who I am, because they check your California driver's motor license ID, they say, oh, this is you. What's your home address? You update it once. Anybody accessing that California driver's license ID should see only one and only one record for that home address. And the final thing about this is when you have durability, it's absolutely obviously mandatory for when high value, high volume transactions have a lot of money involved. So financial sums are exchanging hands. Its example of this is you can be audited. There's a thing called PCI, and the federal and the SEC will check and say if you made a trade, for example, in a financial system that's trading stocks, and you've said this order went through and it doesn't go through, the actual people running the stock exchange can actually be in trouble here. So put this all in context. Why did this come up? So if an outage in the HA scenario occurs, the recovered database will not have all the data. So the customers can't trust the system, or the application designers have to be extremely pessimistic and constantly doing extra checking at all times, which means you take away the management, the RDBMS part, the database management system part, because you can't trust it anymore. You do more work on the application side. You expect the application programmers to be a lot smarter than they have to be and do a heck of a lot more, and it's slower. So what happens then if you have that trade-off between the system has to have durability, yet I don't want to do a heck of a lot of work because it's going to be slow? What a standard database like MySQL, like Oracle, SQL Server, and us, ClustrixDB, do is you open a write transaction to the disk. You fill that buffer with the information that you're going to write, and then you flush that buffer, what's called a write-ahead log. You don't flush all the data. You flush the change. So if I say I'm going to change this table to that table, I just, if you will, at a very simple level, I put the diff in. This is the change I want to put into the system. And I want to flush that to disk before the transaction completes, and I can get that confirmation from the disk that I've written to the disk. And then I say to the transaction, at the application level, your transaction is committed. So again, I open up the write buffer, the transaction is complete in terms of the system, I tell the wall to flush, and I write to disk, and then I tell the application I have an acknowledgement. This is how, for example, MySQL, SQL Server, Oracle, whatever do it, it's synchronous, 1 to 1 to 1. Every transaction has a complete, has a commit, has a wall flush, and then an acknowledgement to the application. This, for example, next is how a different kind of system works. A certificate, or if you will, durability by network will work. What it will do is it'll open the actual disk I/O buffer. It'll keep on taking transactions to that disk I/O buffer until the buffer is full. So you have to flush the buffer less times. So since disk writes are slow in a system, you get a lot more speed out of the system. What that means is there's going to be a little bit of latency there between I've told the application I'm done and the actual data is stored to the disk. So for example, the product manager at Aurora was describing at reInvent. He says, we're not actually doing disk I/O, we're doing network I/O. So in the case of Aurora, they write to 2 copies and 3 different availability zones. And so they say, since I'm going to write 6 times, I'm going to send 6 communications to 6 input buffers. And I'm hoping one of those guys is going to flush really, really soon. And by doing that, they're kind of rolling the dice and hoping that if you get a full 3 AZ outage simultaneously, I don't lose any data. So there are people right now checking from last week on S3 in East Virginia to see if this actually happened to them, because they rolled snake eyes. The expectation you're going to lose all 3 AZs in a single region is very, very low for Amazon, but now we just saw it happen. But again, here's some of the quotes from that actual YouTube, and it's up there. You can go look at it right here. But we're not doing disk I/O, we're doing network I/O. We keep filling the buffer until it's ready to go, which means the buffer has to be maxed before you write, which minimizes your writes to disk, which means you get a lot more speed out of the system by trading off a little bit of latency between I told the transaction it was committed and I'm actually durable with the wall flush. We consider the write durable when 4 of the 6 nodes we wrote to ACK it. So they send, I sent you the communication, please receive this in your buffer. They say, I did. And we're durable to that point in time when the buffer is full and written to disk. But see, there's a difference between we are durable to that point in time when it's written to disk and when we told the application the transaction committed. It's all happening asynchronously. Here's another example. Durability by network means network or node outage failure on a multi-node RDBMS. So for example, certificate-based replication with Galera. The different nodes can have different copies of data after the node or the database recovery. So the transactions will be rolled back, after the application has been told it's committed. That's how the certificates are able to confirm themselves after a system comes back after a multi-node failure. With the core and base writes in Aurora, if multiple AZs go offline, for example, a region outage, before the data is flushed to disk, the transaction will be in an inconsistent state when the database resumes. The transactions, again, will have to be rolled back, again, after the application has been told it's committed. And again, this is kind of a very big challenge when you have a system that says, I'm supposed to be ACID. So systems, for example, MySQL, if there's a network failure, this means a multi-AZ network failure, which means loss of data after the application has been told data is committed. That does not occur in something like a single node system like MySQL, like Oracle, like SQL Server, or a multi-node system like Clustrix. For example, Clustrix is durable per transaction. The commit protocol requires the wall flush before the acknowledge is sent to the application. And if the application is told data is committed, the data is committed. When the network comes back and the instance becomes visible again, the committed data is still on the disk, and the RDBMS continues the transactional state it had before the outage. So that is an overview of exactly what we're talking about between durable and durable by network. There's a trade-off between that latency and confirmation of your data is exactly there. So if you're going full bore for all speed, we've already made a choice. If you have a relational system, you want to have the data be consistent. You're not doing a NoSQL system that says it's okay for it to be inconsistent for a while because I'm valuing speed over data accuracy. So here's a case where we got into a gray area. In order to get speed, the durability got a little bit shaky. Now, some people ask, if you're going to do all this, if you're going to wall flush to every single transaction, isn't that going to affect this actual speed of the system? It will if you have a single node write master, for example, like a MySQL, for example, like an Aurora. With Clustrix, for example, when you have multiple different nodes all taking writes, it turns out that the more nodes you add, the more writes you can get. So as a quick overview here, taking the largest instance available when we did this benchmark on Amazon, 32 core, which is called innate Excel, all of them kind of hang out the same place, 32 cores of Aurora, 32 cores of MySQL, or 4 nodes of 8 cores of Clustrix. They all hit at the 20 millisecond latency right around 9,000 TPS, 90,000 TPS. And the example here is there's 10 SQLs in there. It's a 90-10 workload. You 9 reads, 1 write. And then we just started adding more nodes. And here's another example of that. When you see it without confusion all over the page, you just keep on adding nodes for more and more and more and more and more write speed. Is there any questions today? One of the things that'll come up when people ask and take a look at this stuff, they say, okay, so the first question is, okay, are you able to get speed out of the system? So that's why I front load here and say, here, look, here's a couple of benchmarks. Another question is, why do you do a 90-10? Isn't the benchmarks out there, for example, 100% reads and 100% writes? 100% reads and 100% writes will stress the system and show, it's kind of like looking, how fast is the car speed when you put it on a test stand? The real question is, how fast can the car accelerate when the wheels are actually spinning and pushing the car? It turns out, for example, in an e-commerce site, most people are not checking out simultaneously. You actually have a lot of people who are looking at the site, they're browsing, they're adding things to their cart, they're going to compare different items. None of those are a write transaction in the same way when you go to the checkout, you're actually purchasing something. Actual inventory has to be decremented. Actually, orders have to be created. So there's different kinds of workload on the system. Writes are much, much harder than reads, but you're not doing 100% writes. And the trick is with systems like Aurora that have a shared disk topology, when you do a write to the system, it actually slows down the read because the read has to wait till the write is complete. So what that means is when you mix writes and reads in the system, a system with a shared disk is actually going to get a lot slower. And so this is highlighting in a real case, in a real world workload, when you do a 90-10 workload, something like Aurora is actually going to be not much faster than MySQL, and it's on their own system. Okay, I think that's all the questions for the day. I'd like to thank you all for attending. And again, so be aware when you're putting your system through its paces and you're looking for speed, you've already made a choice that you wanted to have consistency with your system because you're going to take a relational system. It allows ad hoc queries. It allows your system to have a very solid guarantee that the data you put in it is going to be correct and stay there, what we call a single source of truth. Don't compromise that single source of truth by allowing your durability to be a question mark as well.